I'm here to talk about Varnish, and the title of my talk is actually a small lie. As you said, I've been doing Linux and Debian stuff for a while. So the motivation for Varnish is actually this graph. This graph shows the load time for Norway's largest newspaper back in 2007. As you can see, they were using about 15 reverse proxies at the time. They were using Squid. Not very excellent peak handling. Kind of, yeah, not looking too good. And also, they got more traffic, and they didn't really want to keep buying more servers. So they want something better. So they got in touch with a Danish FreeBSD Köln guy, Heen, who then said, he's a Köln guy, doesn't really do user space code, but on the other hand, it's a good chance to show how you can actually write some fairly efficient code in user space, and basically a bit of show people how this can be done a whole lot better. Yeah, so that was actually a debug slide. And the underlying problem that Varnish is an HTTP reverse proxy. It sits in front of your CMS and caches pages. This graph, it shows the load time from 0.1 second here to 5 seconds here, and the exit rate. This graph is from Wikia, and it shows quite clearly that if your web page is slow, people will not continue looking at more web pages. If you're a newspaper and you make your money in advertisements, that's kind of a problem. If you're selling stuff, that's also a problem, because people are going to look at your front page and then get bored, and then actually leave. It's a bit like walking into a shop and then not getting service. I mean, if you actually need help, that's a pretty terrible experience. And part of the reason why CMSs are slow is that they're trying to do a lot of work. Each time you load a page, it generally needs to access a database. It opens files in the file system. All of that takes ages. It takes easily hundreds of milliseconds. And if you're seeing a couple of thousand requests per second, that's a bunch of service. Somebody compared it to you having each time you went into a newspaper stand to buy a newspaper, you would fire up the entire machinery to print a new copy of a newspaper. Pretty inefficient. So this was part of the problem we were trying to solve. And to do that, it makes sense to actually exploit a modern computer, because most of us have, at least the people who have had CS degrees and stuff, well, you have kind of the classical von Neumann computer with, the buses and all that. And that's not really what the computer looks like any longer. Computer today consists of a bunch of cores, a bunch of caches. Some of them might be kind of persistent caches, also known as disks. It's 64-bit. I mean, even phones are starting to become 64-bit now. And it has virtual memory. And virtual memory is pretty important here, because the way Varnish works is it takes, instead of explicitly paging files out to disk, it just maps the entire object storage. This can be a problem if you're on a 32-bit platform, because then your cache size is limited to about 2 gigabytes. This isn't a problem on 64 bits, where you basically you'll have more address space than you have storage. So to take advantage of the first bit, to take advantages of all the cores, Varnish is massively multi-threaded, usually runs with 1,000 threads or more, where each thread is handling a single request coming from a client. All of these threads are generally pre-created, so you try to do the work up front rather than do the work when you're actually in a loaded situation. Varnish tries to exploit cache locality, so instead of doing memory allocations as you go, you allocate a bunch of memory, a memory pool, and you sub-allocate from that. This also means that you don't get so much trouble with caches being flushed and so on. 64-bit I talked about, virtual memory I talked about. This graph shows the relative performance cost of various operations. Increasing a pointer, really cheap. File system operations, really, really expensive. As in, nowadays we have SSDs, but when this graph was first made, you would actually have to move physical atoms around to read stuff off disk. System calls, also kind of expensive. So we try to minimize the number of system calls, which is where the title comes from. So this only generally shows kind of the relative cost of these things. And if you can do the things up, it's better than the ones at the bottom, obviously. Varnish is, in the sense of HTTP, is actually not a cache. It's an HTTP origin server, which just happens to fetch its content over HTTP. So these caches here, they have to trust whatever comes from here. They have to take, if this one says don't cache, they just have to obey. Varnish sits on the server side, and it's under the control of whoever runs the website. And that means that if you say, yeah, the backend says don't cache, but I tell you to cache, Varnish will happily cache. Varnish's configuration is a domain-specific language. So I'm going to show it in a bit, but it gets compiled to C code and then loaded into the process. Varnish consists of two processes. It has a manager process, which does the startup. It restarts the child if it dies, because initially at least, Varnish was kind of unstable. And it's terrible to just be woken up to just restart the process. I mean, the process can just restart itself. The manager also has the VCL compiler, so it takes VCL, compiles that to C code, which is then compiled using GCC. The parameters are shared between the two of them using shared memory, normal, just an mmap file. And yeah, it also does the watchdog, so it goes, are you there? This goes, yeah, I'm here all the time. Well, every 3 seconds. The cacher process itself, it does obviously it does the exception handling, accept handling and the handling of the threads and all the requests coming in. It also expires objects. It expires object by TTL or when the cache is full. It's also using so this is the last bit here where it hashes. So you can define your own hashing key. So if your URL's only that bit after the first slash matches or matters, you can just put that in your hash. By default, it will use the host or the server IP and the URL. All the logs are in shared memory. This means that if your disk goes full, Varnish will still happily serve objects because it treats this as a circular buffer. And then we have different tools, which I'm going to show, that shows this information in various ways. And they're fairly easy to write these tools. We provide a C library where you can write your own, or there are also some Perl bindings. Yeah, so a small example of ACL. This was one of the first examples posted to the wiki, which was somebody they used Varnish very early on to prevent hot linking. So they didn't want people linking to their images. And the way they do that is we have the VCL receive, which runs, it's the first function that runs. If the URL, regex match, JPEG or GIF, and the refer is not example.com, return an error. It's inspired by C and to some extent the syntax of Perl, but not Perl itself. The implementation is fairly simple. It gets compiled to C code, as I said, and you can also escape to C from this. So if you need to do something that's not provided by VCL itself, you can escape. In version 3, which is the current one, you can also import plugins, which then integrate into VCL itself. So it's all a pretty easy language to see and understand. Other features are instant invalidations. We have ACLs. You can use DNS names, or you can use subnets. Subnet masks also gets optimized and compiled down to basically look at one-on-one octet. And then if the request is ban instead of a get or a post, and the client is one of these, then insert that ban. So ban does not prevent stuff from being cached in the cache. It merely invalidates the content in the cache itself. And the way it does this is by all the objects, they have a reference to the object, to the most recent ban they have been checked against. So before serving a new object, it will be checked against newer bans. So this runs immediately. It will run immediately if you have 1 million objects in your cache. But it adds a tiny bit of overhead to all the objects being served after you have added it, because they need to be checked whether their URL is the incoming URL here. So a small demo. Let's see if I run. Is that easier if I do white on black, perhaps? This is a bit hard because I can't see it myself. Just making sure it's... Okay, so run up a couple of these and then run... So I tell it to use my localhost port 80 as the backend. You can define the backend in VCL, or you can define it on the command line. So here I just do it on the command line. And yeah, you can't really see that, can you? Let's see. Okay, I also need to tell it to listen to port 8000, and then do start. So it now defaults to 100 meg of cache. It's mapped, and So now it's running. I can do get stuff, localhost, port. Here we can see that it comes via Varnish. Otherwise, it's a 403, so it's not actually cacheable. But I mean, it sends data through. Some of the data we can then look at some of the stats. You're able to read this fine, right? Yeah. Yeah, so Varnish stat gives us, if I run that, let me actually run that in a different window, and then we can run the curl in a loop. Yeah, so now we're running curl. We get various information about how many requests and connections and all that, which is quite useful to figure out stuff like hit rates. Right now, because they're all 403s, they're all non-cacheable. Our hit rate is 0. Yeah, the first one is a cache hit, cache miss, but the rest of them, because we got the 403, it actually caches that it can't cache an object. So we got what we call a hit pass object. This is useful to figure out stuff like, okay, yeah, I seem to be serving about 30. This column are numbers. Yeah, this is the last second. This is on average across the lifetime of the process. So I'm doing about 100 requests per second right now. Okay, let's do this. If we then do some of the other tools, we have Varnish log. And that goes a bit fast for us. So that shows, because we're logging using a shared memory file instead of using traditional fprint logging, we can log a lot of information. This basically does not add overhead. So all of this, let's find the start of a request. This is the start of a request where, okay, I have a client on localhost, port this. It sends me a get. Here are some headers. Here's the path we take through VCL, where it will say, okay, we're doing VCL receive. Receive returns lookup. We call hash. It hashes on / and localhost port 8000, which comes from here. So this is the default VCL. And then a bunch more where it will tell us that, yeah, we can't cache this and it's forbidden. And we transmit a bunch of headers to the client. In the end, we have the request end, which includes some timing information. Here it tells us that, let's see, this is the start of the request and this is the end of the request. And we're looking at the request taking basically, yeah, that's about 3/10 of a thousandth of a second. But we can visualize that better by not using Varnish log. But we also have a tool called Varnish hist, which if I run this again, so that shows real time the hits and the timing information. So this is really quite useful when you're looking at your website and trying to figure out, okay, so what's the distribution of, like, what's the response time distribution like? These all show up as hashes because they're cache misses. If we had some cache hits as well, they would be bars instead, or pipes. We have Varnish top. which is actually more interesting to if you tell it that you're looking for a specific tag. So if we look for RX URL, for instance, so it tells us that we're looking at, on average, over the last 60 seconds, currently about 400 for the URL slash and rising. Not very exciting right here because we're only fetching a single URL. But again, you can you can also filter this on the client side and the backend side, which means that you can very easily see what are the objects that hit my backend the most. Yes?
Sorry, what is that number?
Sorry?
What is that number?
That number is the average across the last minute. So it's a decaying average. And yeah, so if we keep this running for a bit, it's going to stabilize at, yeah, I said 100 requests a second. So it should stabilize around 6,000, I think. Hopefully, assume I got the implementation correct there. Yeah.
Does any locking go on to Varnish stat to read stuff from the shared memory?
No. This is both a good thing and a bad thing. It's a good thing because the delivery process is not slowed down by this. I mean, sure, if your system load goes too high, it will be slowed down. But it will not slow down the process unless, apart from that, Varnish won't wait for the readers to catch up. The bad side, of course, is since this is a circular buffer, if you are too slow at reading, you will be run over from behind. And at that point, you're going to lose data. You're going to lose log data. So that's kind of a trade-off. You can't have both. But in general, you can read fast enough that as long as you're not doing more work in the logging itself, you generally are okay. But sometimes we see, for instance, we have also Varnish and CSA, which yeah, Varnish and CSA, which prints out standard NCSA style logs. And that does a fair amount of string processing and some memory allocations and stuff like that. So this one is actually too slow if you have some number of thousands of requests per second. But so it really depends on how much traffic you get. Varnish itself generally runs at wire speed, where we've seen in synthetic tests, we've seen people do 70-something gigabits. In general, if you optimize it well, it will basically run at wire speed at least up to 10 gigs with small objects. This makes for interesting challenges when trying to test the performance impact of changes, because most of the time you're basically just testing whether your network is still fast. And yeah, the switch is still delivering packets at about 1 gigabit, which isn't a very interesting test. So for a while, we ran the tests on some underpowered Atom machines, just for the machines to be slow enough that we actually benchmarked the machines and Varnish rather than the network. Yeah, so Varnish and CSA, very useful if you need that kind of logs. You can also tell it to format stuff in various ways and so on. So, any other tools? Yeah, so Varnish itself also. So here, I'm running it in debug mode, which means it runs in the foreground. In general, you don't want to do that, but it's very convenient when you want to stop and start it like that. What you then do is you use Varnish add. Okay, so I need to tell it to actually use. Let's see. There. Command line. And we can then do param show, which shows us all the different parameters. It shows us how long are we going to wait for clients to actually receive all the data. 10 minutes by default. How many threads do we have? The defaults are we go from 5 times 2 pools, meaning 10, and we max out at 1,000. We also have, we wait 2 milliseconds between creating threads, because it turns out that machines are generally not entirely happy if you try to create like 5,000 threads at once. And we can also do param show. So I wonder what does this do? So you can actually get the documentation for what does this parameter do. And you can change so these parameters, if I change them, they're live immediately. If I run Varnish, let me stop this thing. Okay, that doesn't, there. If I run Varnish stat and we look at the number of threads. Okay, so we currently have 10 threads. Now, if I do param set, that's thread pool men 50. Then we can go, excellent. Why isn't it then creating? That's an interesting bug.
Is it a bug?
Yes, apparently we have a bug. Good thought. Okay, yeah, so it was supposed to then end up with a minimum. No, so it actually doesn't do that because I'm not giving it. Yeah, there's a bug there where it should increase the amount of threads if it's already lower. But what it's actually doing is it seems to be just using it as a lower threshold instead. So yeah, a bug. But we tend to find bugs when we're doing demos. It's always good fun. But it's nearly always new bugs though, so it's all good. Yeah. You can also do things like tell Varnish to dump the compiled configuration. So this is the C code it generates, where you can go, okay, so let me make that slightly smaller. So we have a bunch of structs, we have some, yeah, lots of functions, and then we have the. So this is actually what VCL receive looks like. And everything you see here are just from the default VCL. So it tells us that, yeah, if we haven't done any restarts, then add an X forwarded for header. That string looks slightly strange, right? And that's because we don't, for the string, for these, we actually don't use syscalls strings. We encode the length of the string in the first byte, which is really convenient because then you can just do mem copy instead of doing string copy when you need to copy it. So there's a bunch of micro optimizations in a way like that, but it turns out they actually make a difference. Yeah, so that was a short demo. Let me just close these again. Oops, there. That's interesting because, so my display here currently seems to think that it's in presentation mode. Good thing I'm not only finding bugs in my own code. Okay, so we got to the, yes. Yeah, so we're doing a bunch of optimizations. We're avoiding syscalls, but not all syscalls are actually created equal, and not even all syscalls are syscalls, which is even somewhat strange. We use memory workspaces, so if you looked at some of the parameters, you could see that we had a session workspace, for instance, where by default, it's something like 250K, and that might seem, that's where all the manipulation of strings coming from a client goes on, and it might seem like a waste to allocate 256K for that, but until you actually access it, it's virtual memory. So it doesn't actually, it costs you something in some TLB tables and stuff, but it's actually not a problem, and you don't need a physical backing memory for it. You might do with some of the recent overcommit stuff, but we'll see about that. We do the length counted strings, which I showed. Massive amount of threads. We see people running into about 10,000 threads in some cases. And that's just because there is one thread which handles the entire request from start till end, unless it gets held up. We do request coalescing to the backend. So if you have multiple clients trying to fetch a particular object, and that object takes a little while to come back, we won't send more than one request at a time for the object, which means that sometimes if you're a busy site and this is your front page, you can sometimes then end up with a lot of clients hanging off that single object. Currently, we have a mechanism to work around that, where we will then deliver the slightly stale, so it will be expired, but it will only be like a couple of seconds expired in general, instead of letting all the clients wait. But if that's also something you can choose to use or not, where if you don't use it, you'll easily end up with 1,000 clients then hanging off that object and being kicked off when the request comes in. We don't fight the VM. We let the kernel is pretty good at managing the page cache and stuff. And anything that we do there, it will basically only be suggestions. The kernel is going to do whatever the kernel is going to do. And we can tell it that we are going to need this information soon. We tell it that our access pattern is random, because by default, it will pre-read a fair amount, which becomes a problem when you're doing basically random access into a file, and the kernel suddenly then starts reading about 10 times the amount of data that you actually need, because it does read ahead into the neighboring objects. So that's a good thing to turn off in our case. We try to avoid copying data, so we read, because we use the memory workspaces, we just read the entire request into the workspace and try to do as little header processing as possible. When we schedule the threads, the ones that we used most recently, they're probably still in cache. So it's better to pick them than to pick the ones which have been idle for a while. We pre-allocate the threads. We pre-allocate as much as possible, because trying to do work while you're idle rather than do work when you're busy and trying to deliver objects. And the kernel also has a really neat feature called accept filters, where we call accept on, yeah?
Can you do a prefetch, like if a CMS homepage takes 5 seconds to generate and expires in 5 minutes?
We don't do that in Varnish. I mean, we have external tools that do it. So you can run, which are basically going to go, okay, yeah, this is going to expire soon, and then fire off a request to fetch it. The reason we don't do it in Varnish is that it's actually quite hard to figure out what the request should look like. And we try not, you would then have to tell Varnish that yes, the request should look like this. It should have this user agent header, this accept language header, and so on. Or you need to store a copy of the request that came with the object. Well, that fetched object original and replay that. And that might not be a good idea. So we do that externally in the cases where you want it. In general, it turns out that a lot of people ask for it, and very few people actually need it. There are some cases, especially if you have objects that go into the tens of seconds to generate, you kind of want something like that. But also we have support for ESI, which is edge side includes. So they're like SSI, server side includes, except they happen on the cache. So you can have a template where you say that, okay, yeah, please include this bit here, this bit there, and these different blocks can then have different expiration times. So you can have one bit which is user specific, and you can have the rest, which some parts you might not even cache at all because they might be related to your advertisement stuff, for instance. But the text of an article, for instance, probably doesn't change. And then you can just go, okay, I'll just cache that forever and do active management where you go in and invalidate that particular object when it changes. So it depends on how integrated you want your CMS and the cache to be, where it goes from you can drop this in front of a random web server, like basically what I did, where, I mean, my laptop just runs a stock Apache, to somewhere where Varnish actually becomes part of your application stack, and your application doesn't work unless you have something doing ESI in front. So it depends. Yeah, accept filters, really neat feature where you can tell the kernel, don't actually return until there's some data on the socket for me to read. FreeBSD actually has it even better, where you can tell it that I'm going to do HTTP on this socket. Don't return on the accept until there's an HTTP request there, which is quite neat. It's also kind of crazy, but I mean, doing that kind of checking in kernel space, but seems to work, so, well. Yes? Sorry?
Are you tuning the size of the thread stacks?
Yeah, given the default thread size on Linux is 10 megabytes. It was really painful on 32-bit for the people who were running it there. We also tune it down on 64-bit, just because it's such a ridiculous number. I don't remember the default. Sorry? Oh, yeah, sorry. So the question was about whether we changed the per thread stack size. And yes, we do. Was there another question? No. Okay. Yeah, some other considerations where Varnish, because it sits on the server side, it's under the control of whoever runs the backend. Our mission is also to protect the backend. The backends, they run CMSs, which are generally fragile, and they don't want 1,000 requests a second, because then they'll fall over and not come back for a while. So we try to, you have the ability to coalesce, well, you always coalesce, unless you tell it kind of hard not to. And you can limit the number of connections to the backend. And we have the ability, so, and people sometimes ask if, yeah, do you do DDoS protection? And yes and no. The way we generally do it is by handling the request really quickly. And in some cases, that also means you recognize that somebody is pointing loik at you or some other DDoS tool. You pick up some characteristic in VCL, and then you basically just close the connection on them. And we can close connection pretty quickly. Yeah, so the 7 syscalls, which are a slight lie. Because of these, 3 of them are not syscalls. Get time of day is not a syscall on Linux, even though it's kind of is. And the reason it's not a syscall is that the kernel seems to have a memory page with a continually updated timestamp. And when you call get time of day, then actually what it does, it just copies that value. So it's a bit like how do you solve a math problem? You sit down and think about the problem and write down the answer. So to serve a web page in 7 syscalls, you accept the connection, you read the request, you write the result, and you close the connection. Pretty easy. Yeah, Varnish itself, it's BSD licensed. Well, we're a fairly small community. We're pretty friendly, try to help people out. Happy to take patches. It's open source, obviously. We're also happy to sell support to people. And we have some proprietary add-ons which you can use. We exist on the internet, both on IRC and on the web. And so this graph shows another change for, so this was Norway's largest IT site. They changed from Squid to Varnish. And I'm not trying to pick on Squid here, but they went from this, which they were kind of unhappy with, and they also reduced their numbers by half or third or something like that. So this is 2 Varnish servers, and I think that's 8 squids. And the original case where Norway's largest newspaper went from Squid to Varnish, they went from 14 Squid servers to 2 Varnish servers. And the reason they had 2 was because you want redundancy.
Perhaps this is a dumb question, but what's the gray area above the sort of data graph?
Sorry, the
gray sort of.
Yeah, so the color here, green means no packet loss. Colors, depending on which color, shows some packet loss, and it shows the distribution. So here, when you see the gray, it means you have a lot of variance. Whereas here, I mean, one thing is the drop, but the other bit is that you generally have much smaller variances as well. Yeah, because so this comes from SmokePing, really useful tool. It shows you it does 20 HTTP pings every 300 seconds. So it fires off a bunch of requests and then does the timing on the results.
What version of Squid is that?
Sorry?
What version of Squid?
I don't remember. It's from 2009, so it's a couple of years old.
That's 5 years, you realize, right?
A big couple. Yeah, so any more questions?
Does Varnish integrate with SNMP tools like Cacti or anything like that? Have we got a way of getting data on any performance measures?
Yeah, so the question is whether Varnish includes any, what kind of monitoring tools are included. Varnish itself doesn't include any tools. There's a Varnish Nagios plugin. There's plugin for Moonin, and it's Varnish stat can also output JSON. So it's pretty easy to integrate that with basically whatever you want. There also is a Varnish as an MP project on SourceForge. I played with it ages ago, but not recently. And it seemed to output data, seemed to work, but I mean, I don't like SNMP, so I haven't tested it that much.
Got time for one more question, if anyone has one.
Please.
The obvious question. Varnish, shellac,
Yeah, so Varnish, to cover up, give a deceptively nice surface to something which is actually not so nice under the hood. Yeah?
Anyone else quickly?
I'll also be here the rest of the week, so if you have questions or anything, then come see me. And
From the LCA team?
Thank you very much.
Thank you.